All right, this is the 2016 practice test, continued from number 11. Graph of y equals f of x consists of a semicircle with the endpoints here and here. So let's see, if the endpoints are at 2 and 12, that's 10 across there, so the radius of this circle is 5. What's the value of the integral from 2 to 12? Okay, so first of all, what is the area we're talking about here? We're talking about this, right? It's the area between the curve and the axis. So that is going to be negative because it is underneath the axis. So we need to be careful that when we're doing geometry, as you can see that they have like the negative and positive versions of the different answers. We need to make sure we get the right one. So this is the way I'm going to think about it. I'm going to say, look, I'm just going to do the geometry problem that is like this rectangle minus the semicircle. But that's a geometry problem which is going to give me a positive answer. So I'm going to do negative sign and then like rectangle minus semicircle. That's how I'm going to do it, right? Because rectangle minus semicircle gives me the positive version of this, but it's underneath the x-axis, so calculus area would have to be negative. All right. If you want to distribute that sign, you're like, oh, well, that's the same as semicircle minus rectangle. Sure, we can do it that way. So I think I'm just going to leave it like this because I think that's going to match up to this right here. Minus, so this is 6 by 10. And then the semicircle is a circle of radius 5 pi r squared. That'd be 25 pi, so half of that. So sure enough, that's the same as that right there. Number 12, an object moves along the straight line so that any time t, its acceleration is this. At time 0, its velocity is this, and the position is this. And they want to know what's the position at time 2. So to get from acceleration like back up to velocity and then back up to position, I have to do integrals, right? So here, what is the antiderivative? The acceleration is equal to the integral of velocity. And I'm going to have a plus c there, right? Because I don't know what the initial velocity is. Well, I do. I'm going to use that in a second. So the acceleration, oops, I have those the wrong way around. Sorry, velocity is equal to the antiderivative of acceleration. So velocity is 3t squared plus c. And I know that the velocity at time 0, the velocity is 10. So that just makes the c equal to 10. So the velocity is 3t squared plus 10. And then if I want to get back to the position, then position is the antiderivative of this, which is t cubed plus 10t plus c. And I know that when I plug 0 in, at time 0, the position is 7. So when I plug 0 in here, 0, 0 plus c, the position is 7. So that c is equal to 7. All right, and they want to know what's the position at time 2. That'd be 2 cubed plus 10 times 2 plus 7 is 35. Number 13. If y equals this, then the third derivative is, well, one derivative at a time. So dy dx would be the derivative of cosine is negative sine minus the derivative of natural log 2x is 1 over 2x times the derivative of what's inside. So I'm going to simplify that. And that's the 2's cancel out, and that's minus 1 over x, but it's more friendly for calculus to write it like that. So the second derivative is the derivative of minus sine is minus cosine. The derivative of minus x to the minus 1, so derivative is subtract 1, kick the exponent out to the front, and then subtract 1 from the exponent. And then third derivative of minus cosine is positive sine, kick the exponent out to the front, drop the exponent. So it looks like sine x minus 2x to the negative 3, same as that. Number 14, here's a graph of f. It consists of 1, 2, 3 line segments. If the function g is an antiderivative of f, g is an antiderivative of f. That means f prime equals g, right? G is, nope, sorry, that's the wrong way around. G prime is the same as f, right? G is an antiderivative of f. G is antiderivative of f. So take the derivative of both sides of that. I think it's a little tricky to process that and make sure that we have that the right way around. So that's true. We see lots of problems where they like to give us a graph that's the derivative of something. So this is really the graph of g prime. And we know that g of 2 is equal to 5. How many values of c between 0 and 6 does g of c equal 3? All right. That's an interesting question. Oh, there could be thunder coming. I think I saw a flash of lightning. Wait for it. Let's see. G, I'm going to find what these endpoints are equal to. What's g of 0? To find g of 0, I would have to do, since this is what I know about here, I would have to do the integral from 0 to 2. Why am I choosing 2? Because that's the one I know about here, of g prime x dx would be equal to fundamental theorem of calculus, that's equal to g of 2 minus g of 0. Why am I doing this? Because I want to know what g of 0 is. And this, since this is the graph of g prime, I can just get from the graph, that's that area. It's a 2 by 2 triangle, so that's equal to 2. G of 2 is 5, so g of 0 is equal to 3. Oh, that's interesting. Okay, so g of 0 is 3. And then what's happening with the g function? Well, it's increasing since this is g prime. G of 0 equals 3, and then it goes up to 5, and then it goes down to, that's the exact same area here, so it decreased the same amount, got back to 3 there, and then it decreased some more, right, because this is still, g primes are still negative, and then it increased, and it looks like this area is bigger than that, so I think it got back to 3 again. So I think that it's, I think that g of 0 is equal to 3 times. I think it's here, here, and then, I don't know, somewhere in here it's going to cross back, right? So I'm looking at these slopes. If g of 0 is equal to 3 here, and then it goes up to g of 2 is 5 because it's increasing. Those are positive slopes. And then it decreases the same amount, gets back to g of 4 is equal to 3, and then it decreases a little bit more. Those are negative slopes underneath the axis, and then it increases, but it increases, if you look at this area, it's bigger than this area, so it's going to pass 3 again. So 14, I think, is D, 3 times. That's tricky. Number 15. Let f be the function defined above where c is a constant. If f is continuous, these two pieces have to link up. That means if I plug a 1 in this and I plug 1 in this, I got to get the same thing. If you're like, wait a minute, how come you're plugging 1 in that? There's no equal sign there. Well, I'm seeing if the open circle part and the closed circle part link up with each other. So even though this is the open circle part, I need to know where the open circle is. There's the thunder. And I'll see if those two are in the same place. If they are, it's continuous at x equals 1. So plug 1 into this, I get 6 plus c. Plug 1 into this, I get 9 plus, the natural log of 1 is 0. I hope you know that. So c has got to be 3, which is answer choice B. Hey, slope fields. These are so easy. If you know what a slope field is, you know how to do this. You just got to test a few values here. Okay, so let's see. I have this differential equation. So let's test some values and see what's going on. It looks like all of these at the origin have the right slope of 0. So that's not going to help me. So let's look for some places where they're different. It looks like this one right here, I'm looking at the point -1, 1. Negative 1, -1. If I plug in -1, -1, I should get a slope of 0, right? Because -1 squared is 1 plus -1 should be 0. So I'm looking here. Is this where you have to start this problem? No, but you got to pick somewhere and start kind of like sniffing around to see if it looks right or it doesn't look right. So you might have figured something different than me, but what I just figured out is that at -1, 1, I have to have a slope of 0. It would also be true at the point 1, -1. I would also have to get a slope of 0. So let's check that out. So at 1, woo! Wow, that was a bolt of lightning. 1, -1. I would have to have a slope of 0. So that does not look right. At a slope of 1, so that looks right. So I just picked a couple points. I got lucky, or maybe I have a lot of experience and I'm pretty good at picking the ones that I should check, but those were easy to check here and easy to spot here. So there you go. There's other ways of telling, but that will work. So 16 is D. Number 17, function e to the 3x minus 5x plus 7 is a solution to which of the following differential equations? So this says to check these, I would need to know what's the second derivative of this and what's the first derivative, and then just plug them in and see if they work here. So what's y prime? The derivative of this would be 3e to the 3x minus 5. And the second derivative would be 9e to the 3x. This is the chain rule here. And then that just goes away. So now I just need to see which one of these equations, when I plug these things in, actually does equal 0. So I'm just going to check them one at a time and see what happens. So to check A, that says second derivative, which is 9e to the 3x, minus 3 times the first derivative, minus 15 equals 0. I think this is it. So if you distribute this, that's 9e to the 3x minus 9e to the 3x plus 15 minus 15 equals 0. That's it. All right. That was easy. You can go through and just check those other ones, make sure that they don't work, but I think clearly, like, this one's going to be close, but that's the wrong sign, and then these ones just, they don't have the 3 in front of that, so that's not going to work. I guess this is probably if you forgot the chain rule. with the 3 coming out. Number 18, if f of x is equal to sine inverse x, then f prime. So you got to know the derivatives of your inverse trig functions. It's just a fact that calculus students need to know that the derivative of sine inverse is this, right? So that is in, let's see, that's probably section 4.3, chapter 4, third section. So what's f prime of the square root of 3 over 2? It's 1 over the square root of 1 minus, the square root of 3 over 2 squared is 3/4. Now that's 1 over the square root of 1/4. The square root of 1/4 is the square root of 1 over the square root of 4, and 1 over 1/2 is equal to 2. 18 is D. This limit as x approaches e, if you're a calculus student and you're looking at a limit, well, there's different things that we need to know. This doesn't really look like one of those old school chapter 2 limits. This looks like the definition of the derivative. And it looks like the definition of the derivative, remember that limit as x approaches c of f of x minus f of c over x minus c. This is the definition of the derivative of a function at that point. So let's kind of piece together what's going on here. So my function here is this, right? F of x is equal to x to the 20th minus 3x, and the c, the thing that we're plugging in, seems to be e, right? I'm plugging e in for x. So that's the definition of f prime of c. So if I can find f prime of x and then just plug this in, I should say that c equals e, not x equals e. So that's easy, right? So f prime of x is equal to 20x to the 19 minus 3, and f prime of, if I plug e in, then I get 20e to the 19 minus 3, which is b. Don't be a fool now. Don't be picking this because you're like, oh, 0 over 0, that's non-existent. Wrong. 0 over 0 is indeterminate. It means there's more work to do. All right. Last one for this part of the video. Let y equal f of x be a twice differentiable function. What does that mean? It just means that everything you want to be true about derivatives and smoothness of curves is true. That's all it means. Such that f of 1 equals 2, and the derivative is this. What's the value of the second derivative at x equals 1? Okay, so this is the first derivative, so let's take the derivative of it to find the second derivative. Now when I take the derivative of something with a y in it, a dy dx pops up. That is called implicit differentiation. That's, we did that in section 4.1. So I just put a plus 0 there. Never mind that. So the second derivative at x equals 1. So when x equals 1, y equals 2, right? This is the point 1, 2. Xy is 1, 2. So when I plug here, if we want to know at x equals 1, when x equals 1, y equals 2. So I plug that in there. So 3 times 2 squared. And then what's dy dx when we're at this point? Well, dy dx is y cubed plus 3, and y is 2. So 2 cubed is 8 plus 3 is 11. So looks like I've got 3 times 4 times 11, which is 12 times 11, which is 132. Sorry, there's some math.